Have you ever wondered what makes fireworks glow with brilliant colors? Or what helps make our bones strong? The answers can be found in a special family of elements on the periodic table. This family is called the alkaline earth metals. They live in the second column, or group 2, of the periodic table. They are a fascinating bunch of elements. Learning about them is not just for scientists. It helps us understand the world all around us, from the ground beneath our feet to the stars in the sky. This essay is your guide. It will help you explore these amazing metals for your next exam. Let's meet the family members. First, we have beryllium, with the symbol B. Then comes magnesium, or Mg. Next is calcium, K, a very famous element. Following that is strontium, St. Barium, Ba. Finally, at the bottom, we have radium, or Ra. Each one has its own unique personality and set of skills. They are all metals, typically shiny, and good at conducting electricity. But the most important thing they all share is a secret hidden in their atomic structure. Every single one of them has 2 special electrons in their outermost shell. This seemingly small detail is the key to understanding everything about them, from their name to their behavior. So, let's break down that name. Alkaline earth metals. Why those 2 words? The name is a direct clue from history, pointing to how early chemists first encountered and classified these substances. Let's start with alkaline. The alkaline part comes from their oxides and hydroxides, compounds they form with oxygen and hydrogen. When these compounds mix with water, they create solutions that are alkaline. On the pH scale, which measures acidity, anything below 7 is acidic, 7 is neutral like pure water, and anything above 7 is alkaline, or basic. These solutions turn litmus paper blue and feel slippery to the touch, classic signs of an alkali. You've probably encountered this property in everyday life. Many antacids use calcium carbonate to neutralize stomach acid. And milk of magnesia? That's simply magnesium hydroxide suspended in water. A gentle but effective alkaline solution. Now for the earth part of the name. This is an old, almost poetic term from the days of alchemy. To early scientists, an earth was a substance that was non-metallic, insoluble in water, and could withstand the intense heat of a fire without changing. The oxides of these metals, like calcium oxide, fit this description perfectly. They looked like earthy powders and were incredibly stable. Think of plaster of Paris, which is made from gypsum, a calcium sulfate mineral. It's a stable, earthy compound. So the name alkaline earth literally means the earths that form alkalis. It's a piece of chemical history. Now, those 2 outer electrons we mentioned make the alkaline earth metals very reactive. They are extremely eager to give away these 2 electrons to form a stable bond with other elements. Because of this high reactivity, you will never ever find them in their pure metallic form in nature. They are always chemically locked away inside compounds. They're hidden in plain sight within vast mineral deposits, dissolved in the salty brine of the oceans, and form the very bedrock of our continents. To get the pure metal, we have to use a lot of science and energy, often through a process called electrolysis, to force them out of their compounds. It's like cracking open a chemical treasure chest that's been sealed for millions of years. Calcium is a perfect example. It's a superstar of this group, found everywhere as calcium carbonate. This single compound gives us the majestic white cliffs of Dover, the humble stick of chalk, and the beautiful marble used in sculptures and buildings. It is also a fundamental building block for life, forming the mineral matrix that gives our bones and teeth their incredible strength and structure. Magnesium is another giant. It's the 8th most abundant element in the Earth's crust and is found in minerals like magnesite and dolomite. Huge quantities are dissolved in seawater as magnesium chloride and sulfate. And crucially for life on Earth, a single magnesium ion sits at the heart of every chlorophyll molecule, the green engine that powers photosynthesis in plants. To truly understand the alkaline earth metals, we need to look deep inside their atoms, right down to the subatomic level. It's here, in the arrangement of their tiniest particles, that we find the secrets to their behavior. The way electrons are arranged in specific energy levels, or shells, around the nucleus is called its electron structure. Think of it as the master blueprint for an element, dictating everything from its size to how it interacts with other atoms. This blueprint determines its entire chemical personality. For every single group 2 element, the most important feature of this blueprint is the presence of 2 electrons in its outermost shell. These are known as the valence electrons, and they are the key players in all chemical reactions. Let's take magnesium. It has 12 electrons in total. Its electron configuration is 2 electrons in the first shell, 8 in the second, and 2 in the third. Those final 2 valence electrons in the 3s orbital are what define its chemistry. Now look at calcium, with 20 electrons. Its configuration is 2, 8, 8, and finally 2. Again we see that same outer pattern, with 2 valence electrons, this time in the 4s orbital. Do you see the pattern emerging? Both end with 2 electrons in their outermost s orbital. This shared valence structure is precisely why they belong to the same group and share so many chemical properties. It's true for the whole group. Now, atoms are always seeking stability, which in chemical terms means reaching the lowest possible energy state. The most stable arrangement an atom can have is a full outer shell of electrons, just like the noble gases. This is called achieving a noble gas configuration. For group 2 metals, gaining 6 or more electrons to fill their shell would require a huge amount of energy. The much easier path to stability is to simply give away those 2 outer electrons. By doing so, they reveal the full stable shell underneath. When an atom loses 2 negatively charged electrons, it's left with 2 more protons than electrons, resulting in a positive 2 charge. So, magnesium becomes the magnesium ion, Mg2+, and calcium becomes the calcium ion, Ca2+. This single, predictable move, losing 2 electrons, is their #1 play. It explains why they are so reactive and dictates the kinds of compounds they will form. They readily bond with nonmetals like oxygen or chlorine, which are eager to accept electrons. This transfer creates strong electrostatic attractions called ionic bonds, forming stable, crystalline structures known as ionic compounds. The large amount of energy released when this lattice forms, called lattice energy, is a major driving force for the reaction. This leads to familiar compounds like magnesium oxide, MgO, where magnesium gives 2 electrons to 1 oxygen atom, or calcium chloride, CaCl2, where 1 calcium atom gives 1 electron to each of 2 chlorine atoms. It is all in the blueprint. So, to recap, the key is the electron structure. Those 2 valence electrons are always ready to leave, forming a 2+ ion and achieving a stable noble gas configuration. This simple outer shell rule unlocks the predictable and fascinating chemistry of the entire alkaline earth metal group. Now, what do they look like and how do they feel? These are their physical properties. Freshly cut, they are shiny and silvery white, but quickly form a dull oxide in air. That is why magnesium often appears gray. Compared to group 1, they are generally harder and more dense. You can cut sodium with a simple knife, but calcium needs more effort. Their metallic bonds are stronger, so melting and boiling points are higher than group 1. The chemical reactivity describes how readily an element reacts. For group 2, reactivity increases as you go down the group. Barium is much more reactive than magnesium. Magnesium is more reactive than beryllium. Atoms get bigger down the group. Outer electrons are further and more shielded, so easier to remove. Ionization energy decreases. Less energy means easier reactions. With water, beryllium does not react. Magnesium reacts slowly in cold water, but faster with steam. Calcium fizzes. Strontium and barium react rapidly. Magnesium burns in oxygen to form magnesium oxide, a bright white flare. 2 memgros plus O2 yields 2 memgro. Drop calcium into hydrochloric acid and you get fizzing hydrogen gas and dissolved calcium chloride. Ca plus 2 HCl gives CaCl2 and H2. With water, calcium forms calcium hydroxide, slaked lime, used to neutralize acidic soils. Their oxides and hydroxides are basic and can neutralize acids. These simple patterns and equations are the foundation of Group 2 chemistry. Section 7, From Rocks to Rockets, the incredible uses of Group 2 metals. These elements are not just entries on a chart, they are fundamental building blocks of our modern world, found in everything from our bodies to the farthest reaches of space. Let's explore their diverse and vital applications. First, magnesium. Its claim to fame is an amazing strength-to-weight ratio. This makes it perfect for creating lightweight alloys used in high-performance engines, aircraft frames, and even the casings of laptops and cameras. And when you see a dazzling, brilliant white light in fireworks or an emergency flare, that's pure magnesium burning with incredible intensity. Next is calcium, the bedrock of our infrastructure and our biology. When limestone, which is calcium carbonate, is heated, it forms the basis of cement, the material that gives us towering skyscrapers, sturdy bridges, and endless roads. But its role is even more personal. Calcium is the mineral that gives our bones and teeth their strength and rigidity. On a microscopic level, calcium ions are the critical messengers that allow our nerves to fire and our muscles to contract. Strontium and barium are the artists of the group, painting the night sky. Strontium salts, like strontium carbonate, are responsible for the brilliant, deep red colors you see in fireworks. Barium compounds, meanwhile, provide the vivid, ghostly greens. Barium also has a crucial medical role. While barium itself is toxic, barium sulfate is incredibly insoluble. This means you can safely drink it, allowing it to coat your digestive tract and act as a contrast agent, making your organs visible on an X-ray. Beryllium is the specialist, prized for a unique combination of being extremely light, incredibly stiff, and stable over a wide range of temperatures. These properties make it invaluable for high-tech applications, like building lightweight satellites, components for supersonic aircraft, and the massive, precise mirrors of advanced space telescopes. And radium, the last member, has a more cautionary tale. Its radioactivity made it glow, so it was famously used in luminous paints for watch dials and instruments. However, the severe health dangers were soon discovered, and its use was rightly abandoned. This brings us to a vital topic. Section 8. Handle with care. Important safety notes. While these metals are useful, they must be respected. The compounds of magnesium and calcium we encounter daily, like in antacids or our food, are generally safe. However, the pure metals are a different story. Especially as fine powders, they can react vigorously with water, releasing flammable hydrogen gas, which poses a significant fire risk. Beryllium is a serious occupational hazard. It is toxic, and inhaling its dust or fumes can lead to a chronic, incurable lung disease called berylliosis. Strict safety protocols, including specialized respirators and high-grade ventilation, are mandatory when working with it. For this reason, you will never handle pure beryllium in a school laboratory. Radium is dangerously radioactive. Its handling requires extreme precautions. The tragic story of the radium girls, factory workers who ingested deadly amounts of radium while painting watch dials, was a horrifying lesson that led to the development of modern occupational safety standards for radioactive materials. Section 9. Ace your exam. Let's consolidate the key facts. Group 2 consists of beryllium, magnesium, calcium, strontium, barium, and radium. The defining feature of every element in this group is that they all have 2 electrons in their outermost shell. To achieve stability, they readily lose these 2 electrons, forming positive ions with a 2+ charge. And remember the most important trend. As you move down the group, the atoms get larger, and they become more reactive. Time for a quick quiz. Q1. What is the chemical formula when calcium reacts with chlorine? It's KCl2. Q2. Which element is more reactive with water, barium or magnesium? Barium, because it's further down the group. Q3. Name a key use for calcium carbonate and barium sulfate. KCO3 for cement and BaSO4 for medical X-ray contrast. Q4. Why is beryllium used in space telescopes? Because it's lightweight, stiff, and thermally stable. Q5. What charge do alkaline earth metals form when they become ions? They form a 2+ ion. Great job. Good luck on your exam and, study well.